In this lesson, we discuss indefinite integrals and the substitution method. So let's say we are asked to find the integral of this product, x cubed plus x times, or actually that raised to the fifth power, and then times 3x squared plus 1 dx. I would like to show you how we can use the substitution method to evaluate this integral. So what I'm going to say is I'm going to choose a letter of our alphabet other than the letter X because it's already being used. The most common letter I think chosen in this context is U, but that doesn't really matter. So let's say U. I'm going to let U equal x cubed plus x. This is the first expression inside of this grouping symbol, x cubed plus x. Now the reason why I think that's a good idea is because when I differentiate u with respect to x, that is du dx is equal to 3x squared plus 1. Furthermore, this implies that du is equal to 3x squared plus 1 dx. So notice that when I make u equal x cubed plus x, this expression right here, when I make this choice for u, this substitution for u, then I get that du is equal to 3x squared plus 1 dx. That is to say, I get the second part of this that I can replace with du. That's super convenient. So now what we can say is our original integral is equal to the integral of u to the fifth power du. And I can integrate so much easier, right? So much easier. This is simply u to the sixth over 6 plus c. All I have to do now is back substitute. Remember that u is equal to x cubed plus x. So then this is x cubed plus x, that raised to the sixth power all over 6, and then plus c. That's the answer. So using the substitution method, being really clever about what you let u equal will allow us to integrate so much easier. Let me see if I can illustrate this again for us. So imagine we have the integral of the square root of 2x plus 1 dx. All right, so let's make a substitution. So I'm going to say let u equal the radicand, 2x plus 1. I think that's a good idea because, let's see, du dx, the derivative of u with respect to x, would be 2. That is to say that du is equal to 2 dx. So what we can do is now, making our substitution, this is equivalent to the integral of u raised to the 1/2. Now, dx here is equivalent to, well, I guess I should keep going here. This statement here says that du over 2 is equal to dx. So here, when I see dx right here, my original differential, I can replace that with du over 2. So I'm going to come up here and replace dx with du over 2. That is to say, it's equal to the integral of 1/2 u raised to the 1/2 du. We can factor out the 1/2 and say this is equal to u to the 3/2 over 3/2, of course, plus c. All I need to do now is simplify a little bit and also back substitute. Remember that u is equal to 2x plus 1. So furthermore, 1/2 divided by 3/2 is equivalent to 1/3. So then this is 1/3 times 2x plus 1 raised to the power of 3/2 plus c. Again, we see that the substitution method works really well for these types of integrals. Let's look at another. So let's say we are asked to find the integral of secant squared of 5x plus 1 times 5 dx. Let's see what happens when I make my substitution. Let me say my instinct says let u equal 5x plus 1. Now, that would imply that du dx is equal to 5. That would imply that du is equal to 5 dx. Well, that's good because 5 dx is what I have here, and so I can replace all of that with du. All right, so what do we have, folks? We have, let's see, this here is equal to the integral of secant squared of u du. Remember that it is the tangent function whose derivative is secant squared. So then this is just tangent of u plus c. That is to say, tangent of 5x plus 1 plus c. Isn't that great, folks? Let's continue to look at these. Let's look at the integral of a cosine of 7 theta plus 3 d theta. Okay, so my instinct is saying we should let u equal 7 theta plus 3. If that's our choice, then du d theta is equal to 7, which implies that du is equal to 7 d theta. I notice that I don't have 7 d theta, I just have d theta. So I'm going to isolate d theta by saying du over 7 is equal to d theta. Okay, so with this substitution, this integral here becomes the integral of cosine of u du over 7. Now, this over 7 business can be, it's a 1/7 factor, right? So this is 1/7 times the integral of cosine of u du. Now, it is the sine function whose derivative is cosine. So then this is 1/7 times sine of u and then plus c. And of course, let's not forget to back substitute. So then this is 1/7. Remember that u is equal to 7 theta, I believe, right? Where is it at? There it is. U is equal to 7 theta plus 3. So sine of 7 theta plus 3 and then plus c. Man, this is so much easier now that we are making a substitution. Now this next example is pretty interesting. They want us to find the integral of x squared times cosine of x cubed dx. So the first thing that I notice is that this power of the variable in the argument of this function is 1 degree higher than this variable here that shows up in my integrand. So that gives me a clue. If I let u equal x cubed, then when I differentiate u with respect to x, I'll get 3x squared, which is, pretty much this, right? This is x squared. So what I'm trying to say is, let's let u be the higher power of the variable. So like maybe how about let u equal x cubed. Now if that is our choice, then du dx is 3x squared, which of course implies that du is equal to 3x squared dx. Let's continue because I don't have 3x squared dx in my integrand. So let me divide both sides by 3. So du over 3 is equal to x squared dx. And I do have x squared dx in my integrand. You know what I mean? And so then this integral here becomes cosine of u times, let's see, du over 3. Not great. Which is equivalent to 1/3 times, now it's the sine function whose derivative is cosine, so then this is sine of u, of course, plus c. And after back substituting, remember that u is equal to x cubed. I had to scroll back up to see that. U is equal to x cubed. So then this is 1/3 sine of x cubed and then plus c. Isn't that great? Now this next example is really great. Notice they are asking us for the integral of x times the square root of 2x plus 1 dx. Now this one's really interesting because of that extra factor of x in the integrand. Earlier we had something similar to this, and we said let u equal the radicand 2x plus 1. But something interesting happens here. This would imply that du dx is equal to 2, which implies that du over 2 is equal to dx. All right, so I have dx in my integrand, or, that's my differential. So dx gets replaced with du over 2. That's fine. And then the square root of 2x plus 1 becomes the square root of u. That's fine. But what about the x? What about this extra x? So what we could do, because we have an extra factor of x, is we can solve this statement right here for x. So if we do, then it would be 2x is equal to u minus 1. That is to say, x is equal to u minus 1 over 2. So what I can do is I can replace this x here with this expression in u, and so the entire integrand will be in u. So let's see. It'll be the integral of u minus 1 over 2 times u, or no, the square root of u, right? And then dx is du over 2. All right, so let's simplify this because this looks pretty sloppy. So this is equivalent to the integral of 1/4 times u minus 1 times the square root of u du. All right, we can factor out that 1/4. So then this is 1/4. And then we can distribute that square root of u so that you have u to the 3/2 minus u to the 1/2. That becomes our integrand, and then du. So then this is equal to 1/4 times, and then this is going to be u to the power of 3/2 plus 1, which is 5/2, over 5/2, minus u to the 3/2, which is 1/2 plus 1, over 3/2. Let's not forget c. Of course, we need to simplify this. So then this is 1/4 times 2/5 u to the 5/2 minus 2/3 u to the 3/2. of course, plus c. You know this plus c right here, folks? Up here should be outside of the grouping symbol. So then it's all of that and then plus c at the very end. All right, very good. All right, let's see. Now we need a back substitute, right? So then this is 1/4 times 2/5. Now remember what we let u be. We said let u be 2x plus 1. So this is 2x plus 1 raised to the 5/2 minus 2/3 times 2x plus 1 raised to the 3/2 and then plus c. Let's continue to simplify a little bit here. So then let's distribute the 1/3, the 1/4. So that becomes 1/10 times 2x plus 1, the 5/2, minus 1/6 times 2x plus 1 to the 3/2, and then plus c. Isn't that great? I want to make sure that you can read that exponent. This is 3/2. Yeah, that's better. Plus c. That's great, isn't it? All right, let's look at one more, shall we? So what about the integral of 2z dz over the cube root of z squared plus 1? All right, so I want to illustrate here that there's different substitutions you can make. So imagine if we say let u, my instinct says go for the radicand, so z squared plus 1. Let's see what that leads us to, all right? So then du dx would be equal, du dz, right? Du dz would be equal to 2z. So then du is equal to 2z dz, which is really good because that's the entire numerator. So then this turns into the integral of du in the numerator, and then this is the cube root of u, which is the integral of u to the negative 1/3. Let me see if I can rewrite that. There. Du. So then this is equal to, this wasn't too bad, right? So then this is equal to u to the 2/3 divided by 2/3 plus c. So then this is, I'm going to back substitute and divide by 2/3 at the same time. So then this is 3/2 times, and then we let u be z squared plus 1, right? We let u be z squared plus 1. It's right up there. So then I'm going to replace u with z squared plus 1, and that's being raised to the power of 2/3. All right, that's our answer. Now, another thing you could have done is done a different substitution. You could have let u be the most complicated part of this expression, which is the entire denominator. So if you, let me just show what that would look like. So let me do this problem again. We get the same answer. But watch this. We could have done it a little differently. So the integral of 2z dz over the cube root of z squared plus 1. Okay, this time around, what if we would have said let u equal the cube root of z squared plus 1? Now, you know what? I think what we should do at this point is cubing both sides. Because, watch, I think if we get rid of this cube root, u cubed is equal to z squared plus 1, right, everybody? And now if we differentiate both sides, the left-hand side differentiated with respect to u would be 3u squared du, and the right-hand side differentiated with respect to z would be 2z dz, right? Now this is really great because now 2z dz is in the numerator, and so we can replace this now with the integral of the whole numerator is 3u squared du, and the denominator is just u. Oh wow, this is really nice, isn't it? So then this is equal to 3 times the integral of just u du. Wow, that's nice. So then this is 3 over u squared, or 3 times u squared, over 2 plus c. That is to say, 3 halves, let's back substitute, u is equal to the cube root of z squared plus 1. But according to this, we have to square it. So then that just becomes z squared plus 1. If you square the cube root, that just means to the power of 2/3, right? Plus c. And this happens to be the same answer that we got before. Let me confirm. Oh, there it is. It's still right up here. So notice that our two answers, you can see them. This answer is the same as what we got here. So the purpose of doing this twice was just to show you that sometimes there's more than, one substitution that might work.